On March 11, 2011, the seafloor east of Japan moved with almost unimaginable force. A magnitude 9 earthquake ruptured beneath the Pacific Ocean, shaking for several minutes and shifting parts of northeastern Japan eastward. Then the ocean withdrew from sections of the coast. Minutes later, a wall of water arrived, crossing seawalls, lifting buildings from their foundations and traveling kilometers inland. Scientists understood the basic cause. The Pacific tectonic plate had been pushing beneath the plate carrying northern Japan, allowing enormous stress to accumulate along their boundary. But one part of the disaster remained difficult to explain. Why had the fault slipped so far near the ocean floor, where many researchers had expected the rocks to deform without producing such an extreme rupture? The answer was buried beneath several kilometers of water and rock. To reach it, scientists had to drill into the fault itself. In 2024, researchers aboard the scientific drilling vessel Chikyu returned to the Japan Trench. Their target was one of the most inaccessible geological structures on Earth. The ocean at the drilling site was nearly 7 kilometers deep. From the ship, the drill string had to descend through the entire water column and then penetrate roughly another kilometer beneath the seafloor. The expedition recovered cores from the rocks and sediments being carried into the subduction zone. Inside those samples, researchers found a layer of soft, clay-rich material that helped explain the earthquake's extraordinary behavior. The layer was only tens of meters thick, tiny compared with the scale of the tectonic plates surrounding it. Yet it created a continuous zone of weakness along the plate boundary. As the Pacific plate descended beneath Japan, this slippery material became compressed between stronger rocks above and below it. The fault naturally concentrated within this weak layer, almost as though a perforated line had been placed through the crust. Most people imagine a fault as a clean crack separating two solid blocks. In reality, major faults can contain crushed rock, fluids, clay, and sediments with very different mechanical properties. Some materials resist movement and allow stress to build. Others slide much more easily once a rupture begins. The composition of a fault can therefore influence not only whether an earthquake happens, but also how far and how quickly the rupture travels. The clay beneath the Japan Trench has exceptionally low friction. During the 2011 earthquake, it allowed the rupture to continue upward toward the trench instead of stopping deep beneath the seafloor. As the fault slipped, the section of crust above it surged toward the ocean and upward. Measurements indicate that parts of the shallow fault moved by roughly 50 to 70 meters. The displacement extended along hundreds of kilometers of the trench. This was not merely a vibration passing through rock. It was a huge section of the ocean floor changing position within minutes. That movement was crucial to the tsunami. An underwater earthquake does not automatically create a devastating wave. The earthquake must displace a large volume of water, usually by moving the seafloor vertically. Sideways movement alone produces much less effect on the ocean above. In 2011, the shallow rupture lifted and pushed the seabed into the water column. The displaced water spread outward as a series of waves. In deep ocean, tsunami waves can travel extremely fast while remaining relatively low. As they approach shallow coastal water, they slow down, compress, and grow taller. The shape of the Japanese coastline further intensified the destruction in some locations. Narrow bays funneled the incoming water, producing run-up heights of more than 30 meters in parts of the northeast. Floodwater traveled far inland across low coastal plains, destroying communities and damaging the Fukushima Daiichi nuclear power station. Scientists had found evidence of weak clay soon after the disaster. In 2012, an earlier drilling expedition reached the fault and recovered material from the rupture zone. Laboratory tests indicated extremely low friction. Temperature measurements also showed that little heat had been generated during the earthquake, consistent with a fault that had slid unusually easily. But the earlier cores represented only a limited section of the geological system. Researchers still needed to understand how the incoming Pacific plate was structured before its sediments entered the fault. The later expedition recovered a more complete sequence and showed that the weak clay layer was not simply a small patch created during the earthquake. It was part of the geology being carried toward the subduction zone. The clay had accumulated over tens of millions of years as the Pacific plate traveled across the ocean. Fine particles slowly settled onto the seafloor, forming sediments that were eventually transported toward Japan. What appeared to be an insignificant layer of ancient mud became a mechanical weakness capable of influencing one of the largest earthquakes ever recorded. The discovery challenges a simple idea about earthquake danger. Risk is not determined only by how quickly tectonic plates move or how long a fault has remained quiet. The materials inside the plate boundary also matter. Two subduction zones moving at similar speeds may behave differently if one contains strong, rough rocks while another contains a continuous layer of weak clay. This could help explain why some enormous earthquakes rupture all the way to the ocean floor while others remain deeper. A rupture that reaches the trench can cause much greater seafloor displacement and therefore generate a larger tsunami than its magnitude alone might suggest. Magnitude measures the total seismic energy released by an earthquake, but it does not provide a complete description of tsunami risk. The depth of the rupture, the direction of movement, the shape of the seabed, and the distribution of slip all influence the resulting waves. A slightly smaller earthquake with extreme shallow slip could produce a more dangerous local tsunami than a larger event whose rupture remains deep underground. Researchers are now investigating whether similar clay-rich layers exist beneath other hazardous abduction zones. One possible comparison is the Sunda Trench near Indonesia, where the 2004 Indian Ocean earthquake generated a tsunami that crossed the ocean and killed hundreds of thousands of people. Scientists have found evidence of weak sediments in parts of that region, although every subduction zone has a different geological history. Other major fault systems remain less well sampled. Drilling kilometers beneath the deep ocean is technically difficult and expensive. A drill ship must maintain its position despite waves and currents while controlling a long pipe that can bend and vibrate. The cores recovered from a narrow borehole represent only a tiny sample of a fault stretching for hundreds or thousands of kilometers. Scientists therefore combine drilling with seismic imaging, laboratory experiments, seafloor instruments, and computer models. Seismic waves can reveal buried layers because they travel at different speeds through different materials. Pressure and temperature experiments test how core samples behave under conditions similar to those inside the fault. Dynamic models then simulate whether those properties can reproduce the slip observed during real earthquakes. The goal is not to predict the exact date of the next major earthquake. No reliable method can currently provide that kind of warning. Instead, the research can improve estimates of what a particular fault is capable of producing. Before 2011, some Japanese hazard assessments underestimated the possibility of a magnitude 9 earthquake along the Tohoku coast. Historical records covered only a small fraction of the fault's geological cycle. The discovery of the clay layer shows why studying the physical structure of a subduction zone is essential. A fault may possess the conditions for catastrophic shallow slip, even if modern instruments have never recorded it before. Better geological models can improve tsunami simulations. If researchers know which sections of a trench contain weak material, they can test scenarios in which rupture reaches the seafloor and produces extreme displacement. Coastal planners can then identify areas that may face deeper flooding or shorter evacuation times. The findings may also improve real-time warnings. Immediately after an offshore earthquake, monitoring systems estimate its location and magnitude. Seafloor pressure sensors and GPS instruments then measure how the ocean and crust are responding. If scientists understand the expected behavior of the fault, they may more quickly determine whether the earthquake produced dangerous shallow slip. Japan has already expanded its offshore monitoring networks since 2011. Cables carrying seismometers and pressure sensors now stretch across parts of the seabed, allowing changes to be detected closer to their source. These systems cannot stop an earthquake, but even a few additional minutes of warning can help trains halt, factories shut down machinery, and residents move toward higher ground. The hidden clay layer does not mean every section of the Japan Trench will behave identically during a future earthquake. Faults are complicated and uneven. Strong sections can sit beside weak ones. Fluids move through fractures, pressure changes, and earlier earthquakes alter the stress remaining in surrounding rock. But the new cores provide direct physical evidence for a central part of the 2011 disaster. The tsunami became so destructive not only because two tectonic plates suddenly moved, but because an ancient layer of soft sediment guided that movement toward the seafloor. For more than 100 million years, microscopic particles settled quietly onto the Pacific plate. The plate carried them across the ocean toward Japan. Eventually, those sediments entered a subduction zone and formed a slippery pathway through the crust. Then, in a few minutes in 2011, that narrow geological weakness helped a rupture travel to the bottom of the ocean. The seafloor lunged forward, the water above it was displaced, and a tsunami transformed the coastline. The discovery is a reminder that the scale of a material does not determine its importance. A clay layer only tens of meters thick helped control the movement of a fault hundreds of kilometers long. By drilling into that layer, scientists have uncovered one of the physical reasons why the 2011 earthquake became such an extraordinary disaster, and gained a new clue for identifying where the next devastating tsunami might begin.